Okay, so we're back. Let's continue with lesson 1. So this schematic um, represents the building performance hierarchy. So what are we looking at? Just as with any building, we are looking first, starting at the bottom with our foundation. What are the essential factors or issues that we need to be concerned about in terms of our building design to ensure proper building performance? And the first thing we need to be concerned about would be health and safety issues. So health and safety issues, you're looking at things like fire resistance, the structural strength and integrity of the building. So all of these things will determine the safety of individuals. You don't want buildings crumbling around you. The health of the building in terms of some of the things we talked about earlier, the ability to keep moisture and heat where it belongs, either inside or outside of the building. So once we have addressed the issues that revolve around health and safety, the next thing you would want to look at would be your environmental considerations. All right, so environment will look at things like heat, moisture, the breathability and the air quality around you. Solar radiation will be concerned with things like heating from outside of the building. How does it affect indoor comfort and air quality, etc.? All right. And once you have addressed these issues in your building design and performance, the next thing would be sustainability. So when we talk about sustainability, what we're doing is we're building on these things that we just looked at here in your environmental considerations, but we're looking at in terms of durability of the building, based on your design and the strength and performance of the building. Is it long lasting? Will it perform well for a long period? The economics, what is the cost of sustaining these operations and this particular performance, as well as the environmental impact, not only inside your building, but remember, as we said before, your building as an object within a system, it has boundaries that may extend beyond that of the building external walls itself. All right, so does your building also affect the community in any way? You want to consider things like that. And then lastly, at the very top of your pyramid, you're looking at things like aesthetics. How does the building look? Is it designed for comfort? Is it designed for good sound, visual, and all of these, the overall well-being of the occupants? All right, so in terms of building performance hierarchy, these are the things that you would need to be concerned about. Note your foundation starts here with health and safety, and then we move upward towards aesthetics. Right, so still talking about building performance. So optimizing performance goes beyond compatibility between the structure, the enclosure, interior, and services. It involves the assessment of the economic, social, and environmental factors so that performance targets are attained affordably within the skill capacity of the industry. All right, so these are some external factors that you would have to look at, and how does the economy of a particular sector or a nation or society influence your ability to put certain things in place to enhance performance. Social, for example, was the skill capacity, what is the need and willingness to participate in a project like that, and then of course your environmental parameters, where you may be looking at things like your landscape, geology, atmospheric environment, etc. How do these factors affect your building performance? So still talking about building performance, now we're trying to put some of these issues and objectives in place, right? Building performance involves numerous interfaces, or in other words, influences between the buildings, its occupants, and the natural and built environment. So if you follow with me on the schematic, we have a nice summary here. On the left side, we have the environmental factors that can influence the performance of your building. And then we have the built environment factors, or the non-environmental, non-natural environment, that is. So as mentioned before, the issues on the ground, such as your soil quality, hydrology, your soil moisture, the landscape, which is your topography. How do all of these things influence the performance of your building? So your building design should be centered around these natural factors here. Then you look at your resources. What natural resources do you have around? For example, do you have a good number of water sources? Especially if you have to be dependent on natural and groundwater resources. What does your landscape look like? Is it flat? Is it hilly? Are you in a valley? All of these things will determine the way in which your building is constructed. And of course, your climate and atmospheric environment will also determine how your building is designed and how it performs. On the right side, infrastructure services. Infrastructure services again may involve your wastewater network, your piped water supplies, electrical infrastructure, internet infrastructure and network that's available. So actually internet may fall into here. Then there's the community. You would have your outside of the occupants of the building, which would also fall into your community, because remember, you are also designing for the comfort and well-being of your occupants. But then you must also consider your external community, how they would be affected as well. Is it a public building that would require the community to have access to it? All of this must be designed into the performance of your building. And then your economy and your markets. This can affect building prices, whether you have skilled laborers that meet the requirements for you to build and design and build your building as needed, etc. All right, so there's a lot going on in this diagram here. So please take some time to study the diagram and review the lecture so that you can place it all in context. And here I have another diagram for you. Now don't get too worried that the diagram is very busy, so I will just highlight to you what I want you to know. So really, this diagram is showing the relationship between the physics, materials, components, and the systems of the building. So remember, we keep talking about the building as a system. So you have objects and you have systems that are all related to each other. So the important thing here is this note. The characteristics of materials, such as the strength and weight of the materials, the components of the building, such as the structure of your building, and the systems, such as things like the buildings, the air conditioning, etc. These must take into consideration the physics of your environment in order to function according to the needs of the community. So we mentioned physics, materials, components, and systems. So each of these are related. So really what I would want you to do is to be able to pick from the list of examples and be able to explain how they're related to each other. Alright, so for example, the physics, as we said, physics of materials, for example, is the nature of your material. Is it combustible, corrosive? Does it vibrate? What level of vibration? How these things, the material itself you're talking about, how dense is your material? If you're talking about corrosion and combustibility, you're looking at other issues such as thermal conductivity, combustion temperature, directly related to the combustion um, phenomena here, and then you go across here to composite properties, the components. Again, you're looking at things like fire rating. So notice we're relating it right across in the context of fire. And then how does it affect your system? Of course, health and safety would be a big issue here, all right, in terms of fire safety. All right, so what I would need you all to do to be able to look at this diagram and pick out any of these characteristics under the physics, materials, components, and systems, and be able to explain to me right through from physics to systems what the relationship is in relation to the functioning of the building. So continuing, heat, air, and moisture flows in buildings or houses. All right, so these are some very important key points to remember here. Heat moves from hot to cold. So within a building, you find heat can move from hot areas in the building to cold areas. So if your goal is to try to cool down the building, now you have a bit of a problem. So that is something that would need to be addressed. Similarly, air moves from higher to low pressure areas, and moisture moves from wetter areas to drier areas. So if you have a concern about mold buildup, you'd want to pay attention to how the moisture is moving if moisture enters into your building. Okay, heat transfer. Right, so we talked about, so the first thing we're looking at is heat transfer. So remember earlier we talked about heat transfer via different methods of convection, conduction, and radiation. So for example, to make it more relatable to you, we have examples, very personal examples of each of these, of how heat can be transferred. For example, convection, cooling yourself by using a fan. Conduction, heat loss through an exterior house wall, most of us familiar with this. And then radiation, cooking food in a solar oven, all right, or even a microwave. All right, that's a type of radiation. So heat can be transferred via methods like that. So let's talk a bit more about air flows in the context of the building. So air needs an opening or a hole to flow through, and also it needs a driving force behind it in order to move it. Alright, so it needs a pathway and a driving force. The air flows within buildings are either controlled or uncontrolled. Examples of controlled airflow, they'll be generated by mechanical devices. For example, you have ventilation systems and fans within your building. Heating and air conditioning system flow. All right, so it's controlled because there is something in place that is designed to direct the flow and to as we said there, to direct the flow and to drive the flow. So it is controlled. Uncontrolled airflow is not designed, is a non-designed movement. All right, for example, it can be caused by wind or by the force of heated air rising within the building, or if you have malfunctioning equipment. So it's uncontrolled. Also, it can be uncontrolled if you have leaks in the air conditioning system, the air distribution system. All right, so it's uncontrolled if it's really by natural forces, or if you have malfunctioning in your HVAC system. Common sources of, so note we've dealt with heat and we've dealt with airflow. Now we're dealing with moisture. So common sources of moisture in your buildings: condensation. This is moisture in the form of vapor, and this will cause mold growth, mildew, staining, poor performance of insulation in your building, etc. All right, then you also have penetrating damp, such as so penetrating damp examples would be damp patches, for example, in your walls or in your carpeting, and this can cause mold growth as well. You can have leakages from pipes, tanks, drains, and so on. Then we have rising damp. Notice this is different from penetrating damp. Rising damp, this is caused by capillary action drawing moisture up through porous elements of your building's fabrics. For example, you may have seen maybe a pipe leaking in a wall. The moisture may have started at the base of the wall, and then you begin to see it rise up the wall. That might be an example of rising damp. Then you have building defects. For example, lack of adequate roof space ventilation. So there should be, I can't give you the specific figure, but your roof really needs to be, there needs to be a specific distance between your ceiling and your roof for ventilation purposes. Faulty retrofit installations, application of paint or plaster that affects the breathability of the building element, and so on. So these are examples of building defects, right? Additionally, you also have indoor moisture sources that can build up the moisture inside your building, such as cooking, bathing, washing, tubs, indoor pools, etc. Alright, so where you have those kinds of situations occurring, where you have a buildup of moisture, you have to also except in the cases where you're looking at occurrences that will require repairs. If in the case of indoor moisture activities, this will have to be addressed in your design of your building plan. Alright, because you will have to look at putting things in place for dehumidifying your building, etc. Right, so moisture flow mechanisms. Right, so how does moisture flow in your building? Gravity, first of all. Gravity moves rainwater down the building's exterior surfaces. If there are openings in the exterior walls, such as cracks, or maybe some of your building exterior fittings like windows, doors, if they're not properly sealed, water will pass through them. Then you also have capillary suction. So another mechanism. Water is drawn in through tiny pores in the building materials, often so small they are invisible to the human eye. So I gave you an example before, for example, where you have moisture in your wall that rises up the wall. Okay, still talking about moisture flow mechanisms. And you have airborne movement of water vapor. So air movement can bring a large amount of moisture into a building if it is not impeded by good construction practices, such as airtight walls, sorry, forgive me. Right, so there must be proper sealing between your walls, and even your walls and your roof and ceiling. You want to seal off those areas. You don't want gaps in the different panels of your building. Alright, so air can move through there and allow moisture in. And there's water vapor diffusion. So water vapor will pass or diffuse through building materials where areas of high vapor pressure and low vapor pressure exist on either side of the wall or the material. So on one side you have high vapor pressure, and on one side you have low, and remember it always moves from high pressure to low pressure. Alright, especially if you have left those gaps available for the vapor to move through. This movement is from, right, as we said, from high to low. Okay, so now we've come to the end of today's lesson, and I leave you with this question. Alright, effective building science results in great buildings, higher occupant productivity, lower operational and maintenance costs, and much smaller carbon footprint. All right, now this question would lead you to today's activity. So at this point, I would like to ask you to please proceed to the activity for today's class. Thank you.